Okay, we have a few more. So this is question 6 continued. We have a few more questions, reactions to finish off. So I've got 3215p, and again I got to balance it out. 32 on top, 15 is equal to 16 minus 1. So go and look up what's the 16th element in the periodic table. It's sulfur. So again, this is a beta minus decay, and technically it should also have a neutrino, antineutrino on there. How about this one? 40 plus 0 is 40. 20 plus 1 is 21. 21st in the periodic table is scandium. And so this is beta plus. And again, it should have a neutrino on. All right, and let's see here. I've got, this one is alpha decay, right? 4,2 helium. So top numbers have to add up. I must have 240. So that 240 plus 4 is 244. I must have 92, so that 92 plus 2 is 94. And I look up element 92 in the periodic table is uranium. Okay, so let's move on now to the last topic of the chapter, which is radioactive decay half-life times. All right, so carbon-14 has a half-life of 5,730 years. Okay, so we call that T1 half is 5730. And we have 12 grams of carbon-14, well, not carbon-14, of any carbon from living matter. So it's going to be made up of all the different isotopes. It decays at the rate of 180 decays per minute due to the radioactive carbon-14 in it. So what is that? That's delta N over delta T. Okay, so that is 180 decays per second. So decays per minute. Okay. And we want to know what's the decay rate of the sample 1,000 years from now and 50,000 years from now. So when it's living, it's got 180 decays per minute. What is it after 1,000 years and after 50,000 years? Okay, so what is our equation? Well, our equation is delta N over delta T is equal to delta N over delta T0, which is what we're given here at the top, 180. That's when it's still alive, times e to the minus lambda T. So lambda is a decay constant. How do we find it? Well, we can get it from the half-life. So we're told that the half-life is natural log of 2 over lambda. So I can rearrange this and get lambda is equal to natural log of 2, or sometimes it's just written as 0.693 divided by the half-life. So if I put that in, natural log of 2 over 5730, I get 1.2094 times 10 to the minus 4. And the units are going to be per year because I've put in my half time in years. Okay, so I've got my delta N over delta T0. I got my lambda, and I'm given the T in part A and part B. So this is just going to be plug and chug. So for part A, T is equal to 1,000 years. So I'm going to do delta N over delta T is going to be delta N over delta T0, which is 180, times e to the minus lambda, 1.2094 times 10 to the minus 4, times T, which is 1,000. And I had to match my unit. So this is, my lambda is in per year, and I multiply by time in years, so the units of years cancel out. And I get 159.5 decays per minute. And B, the only thing different I'm going to do is I'm going to increase my time, make it 50,000 years. Okay, so delta N over delta T is going to be 180 times e to the minus, same number, 1.2094 times 10 to the minus 4, that's my lambda, times 50,000 this time. And I get 0.426 decays per minute. So you can see after 1,000 years, there's not that big of a change in the decay rate, but after 50,000 years, it's gone down by quite a bit. Okay, so carbon-14 is good at dating things from basically from when it first dies to numbers that are 50,000, 100,000, hundreds of thousand years old. But after that, the decay rate becomes very small, and so there's sort of minimal changes as the lifetime changes.